In quantum theory, the central quantity that describes the state of a system is the wave function psi. It depends on the position of all the particles and on time t. For one particle in one dimension, it's psi of x and t. A wave function is a solution of the time-dependent Schrödinger equation. And the wave function is a statistical function that provides a statistical description of the state of a quantum system. From the wave function, the averages of position x, linear momentum p, kinetic energy t, and all other dynamic variables can be calculated. Averages are also called expectation values. What is the meaning of the wave function? The answer is given by Max Born's statistical interpretation. It says that the wave function times its complex conjugate, psi star of x and t times psi of x and t, or equivalently its modulus x and t squared, is associated with the probability of finding a particle at position x. More precisely, it is the probability density of finding the particle at position x. The integral of this probability density psi star psi over a spatial region between A and B is the probability of finding the particle between A and B. At time t. Based on this statistical interpretation, the wave function itself, psi of x and t, could be called a probability amplitude. Visually, the Born interpretation looks like this. Graph psi star psi against x. In regions where psi star psi is small, you are unlikely to find the particle. In regions where psi star psi is larger, you are more likely to find it. The area underneath the curve between A and B is the probability of finding the particle between A and B, which is a number between 0 and 1. Based on this statistical interpretation of the wave function, we say that the particle is delocalized. This does not mean, however, that you can say anything about the position of the particle before you actually do an experiment and measure it. Quantum theory is a statistical theory. Even if you know everything the theory can tell you, you still cannot predict with certainty the outcome of a simple experiment. The only thing you get from the wave function is statistical information about the possible outcomes, about what you would get if you performed the experiment on each of a large set of identically prepared systems. This is a profound indeterminacy inherent in quantum theory. It is very counterintuitive, but this is how nature seems to behave.